as mentioned, my name's Estefania, I go by Esti, and essentially today I'll be presenting a little bit of bi-level optimization. And to give a bit more context on it, there will be a little more generalness to the nature of this presentation. This is more something, a little more research based that is recent for me for solving the problems that I'm looking at. So I'll kind of talk a little bit about that, and then I'll also contextualize it in terms of our problem and bringing it all back at the end. Sorry, give me a second. I think I've got a bit of lag. Okay, so just to introduce the talk for today, essentially the purpose of this talk is more about engaging in the optimise expertise. Since there's a lot of different people working in a lot of different optimization spaces, I kind of wanted to take this as an opportunity to bring that all together and have everyone kind of communicate about where we can see, different parts of this problem being solved, because this is a really, really big, I think moving forward is going to be a growing topic, as with all operations research topics. So the way I'll go through this is I'll first start off by giving a couple of problems for context. So I'll start with air defense and then in fire response. After that, I'll actually introduce bi-level optimization itself with some definitions, a few just smaller examples, some present methods for how they're solved at the moment, and then existing challenges, or at least some parts of the challenges. And then the present real world approach we're using, and then hopefully we'll have a good set of time to actually have a discussion about it. I think the most important thing about this today is I'm going to try and keep it a little more high level at certain parts. I won't get too delved deep into the research, because I kind of want to talk about it from this practical, like the more practical perspective. So let's start with the air defense problem. So imagine if you have this air defense problem where you have an asset that you're protecting. So in the bottom left-hand corner there's an asset that we're trying to prevent an enemy from destroying. Now, the enemy is coming from the right-hand side. There are parameters that guide what kind of weapons are being fired at us by the enemy. So what are the threats? So these might be, obviously, they might be like faster missiles, they might be slower missiles, they might be helicopters. But at this stage, pretend that it doesn't matter, right? From there, we have a sensor that has a detection range. And the placement of this sensor will determine how quickly we actually detect these threats. But obviously, that's conditional on where the threats are actually starting from. So if you imagine where the sensor is placed here, the threats are detected with a lot more, we have a lot more of an early response about where they are, which gives us more time to actually correct ourselves. And it also gives us more time to determine what should we actually be allocating to best neutralize that threat. Now, if you imagine we have a sensor that's close here to where our weapons are, then by the time that we actually detect the threat, we may not have enough time to actually decide on the optimal combination of weapons to actually fire. So it's quite imperative that we have the sensor placed at a good location. Now, that looks like one static optimization problem, but actually there's two, right? So there's two problems that are nested within each other. The first one is that the sensor placement will actually determine how soon it's able to identify threats. And then there's actually a weapons allocation that occurs here. And in the real world scenario, we'd be talking about a dynamic optimization. We'd be trying to identify the optimal at the end of that scenario where the sensor is placed there. So there's two optimizations that are occurring where one is dependent on the other to give it constraints. The sensor placement will constrain a scenario which this will exist within. So if it's not clear yet, it will be a bit more clear as we go through some other examples. So again, this is a class of, I guess it's a class of optimization problems that have very similar, there's similarities in how they behave. And another example of that is fire response. So in this case, consider that there's, in the left-hand side, there's an original fire rescue service structure. So it's how the service station is actually set out, and everyone moves in a single team. So the teams work together. So you can see here, there's the full-time fire station and a part-time fire station. And when there's an accident there, it's determined who gets sent out, which team gets sent out to go and, try and, mitigate the damage of that risk. Now, in a future setting, there's the consideration of, okay, well, how can we actually best allocate who is going to the fire rescue site? Because we may not, sometimes we might only want to send a first response unit who will actually determine if there's a real problem, because we don't want to commit all of our resources, all of our, water units, if it actually turns out it's just a tiny fire that can be managed or mitigated in a much smaller setting. So in that case, there's, this new optimization that's occurring. And that optimization is we're trying to allocate the units that are actually being used to solve or to mitigate risks in accidents. But simultaneously, the other thing that will actually impact that is, where are we placing these fire stations? Because depending on where these fire stations are placed, the response times will be different, right? Depending on where you're actually keeping or where you're hosting the full-time station and the part-time station, that impacts what resources are available where. So that in itself is an optimization. Now, from this, there are probably other optimization problems that you can see emerging. And that's because I think oftentimes when we're dealing with real world problems, there's actually so many different perspectives from optimization. When we work in a theoretical setting, it's a lot easier to say, okay, like I'm solving this specific problem where I'm trying to find this, specific outcome, and I build algorithms to solve for it or whatnot. But in the real world, there are so many different perspectives you can look at. So, someone might want to look at it as a dynamic optimization problem. Someone might want to look at it as a resource allocation problem, but someone might want to look at it as a different kind of problem. And that's kind of an important thing to keep in mind when we're looking at bilevel optimization. So when I talk about bilevel optimization, you would have seen in the earlier two examples that there are two optimization problems that are coexisting. And instead of just coexisting in a way where, one is happening and then another happens alongside it, it's actually that one of them creates constraints for which the other is then able to make decisions, right? So there are two optimization problems that are actually nested within each other in a hierarchy. Now, again, problems in optimization, we often study them in isolation, which is that, we try to look at it from a dimension that says, well, how can, so for example, if I'm looking at a bi-objective problem, I might just look at it from this perspective of, okay, how can I isolate the objectives that I want to, the objectives that I specifically want to optimize, and then just work at optimizing that. But actually in a lot of real world settings, we have ones where there's a bit of an iterative process, right? And I'll come to a couple of those examples, but what happens is when you optimize, someone else will actually optimize something too. And so you have to take that feedback and then re-optimize, and then they will optimize themselves too. So instead of just you being the only decision maker and you being the only optimizer, there is someone else at the other end who's optimizing while you're optimizing. And so there's in some cases they're adversarial, in some cases they're not. But in the previous two examples, the optimization of the location is what we call the upper level, right? It's the upper level optimization in that it becomes a constraint that fixes into the lower level optimization problem. And that's also, we also call it like a follower and a leader. So the leader is the one who creates the constraint for the follower, who will then optimize within that space and then feed that back up. So some other examples of when this happens is in transportation. So in setting tolls. So an example of this would be the placement of a toll. Obviously, when the government places a toll road, there's going to be a reaction. It's not just once it's placed, they can optimize everything perfectly and go, oh, I'll make this amount of money. Because what happens is people will start avoiding those toll roads, and that will then have flow-on effects. So then there's, the problem of toll setting. At what price point do you actually set these tolls to be able to maximize how much money you make from a social welfare perspective? Because there's no point in placing a toll road with, the best intentions and then the reaction not actually playing out the way you want it to. Energy, again, so the placement of where they put grids, because obviously there's a feedback that will happen with how people are using electricity. There's also environmental economics, again, establishing taxes for pollution. You want to tax people enough so that they, you can offset the pollution that's being generated, but you don't want to simultaneously do it to the extent where no one wants to do anything. And then in defense, there's the Stackelberg game. So this is in game theory context where they talk about like an adversary, where if I'm trying to make a move, you can think about it like at a chessboard, right? If I'm trying to win in a chess game, I have an adversary who is also trying to win. And so we're constantly trying to preempt each other, and we're trying to optimize our move sets ahead of time with the anticipation of what the other person is doing. You can't just optimize your entire chess game at the start and then run it. You always have to be taking into account this, this reaction of optimization that's happening against you. And then, of course, there's machine learning as well, where, they talk about minimizing the number of features in your model while still, minimizing your classification error rate, because those things, again, they don't happen at the exact same time. One happens first and then the other happens as a consequence to the earlier optimization, the number of features in that case. So again, in all of these settings, there's always a leader and then there's a follower. The leader will always set the regulation and the follower will make reactive decisions, which then feed back to the leader. So hopefully that's an overview. Now, in terms of the definition of how it works, this is just a simple definition. Essentially, you're trying to minimize this overall, this is what we call the leader's objective function. It takes into account the decision variables for the follower, so the lower, and the upper, which is the leader. And that's subject to trying to find the optimal for you're trying to find the optimal solutions for the lower, or the followers in this case. So basically the idea is that if you are able to get the optimal performance of your follower, then the leader should be using that to create their best solutions, right? And in that case, there's two splits to look at this from. So there's the optimistic perspective, and in the optimistic perspective, it means that the follower and the leader are both, they both are in harmony, right? It's the belief that the follower will want to do the best thing. It'll choose a solution that will be best for the leader. Whereas in the subsequent one, this is more about the Stackelberg games where they're adversarial. So instead, in the pessimistic case, the upper level has to actually take into account that the lower level, the follower, is actually going to try and do something that will give it a worse outcome. So now they're trying to anticipate each other. So of course, that's subject to constraints, but what you'll see is that the constraints of the upper level will always, it will always constrain into the lower level. But there are cases where it can actually be both ways, right? They can actually constrain each other. There's linkages between the two. So this is a more graphical diagram representation of it. So what happens is when you have a decision vector from the upper level, you feed it straight down. So if you imagine this is the entire decision space, that feeds directly down into the lower level. And so the lower level will have its own surface and its own decision space. And then based on that scenario that is being fed into it by the constraint of this. So instead of being constrained by all of this, only this point is the constraint. It gets fed into the lower level problem, which will optimize, in this case here, for that level. And again, in the context of optimistic, we're assuming that this point here will be the point that will best serve the purpose of the upper level. But in pessimistic optimization, that's not the case. So the present methods for solving these kinds of problems, I guess there's a bit of consistency in how we perceive these things, because there's the single level reformulation, which you can think of a lot like how in multi-objective optimization, they try to transform it into single objective optimization. So in this case, if it meets specific conditions, like there's a convex lower level problem, then you can transform it back to a single level. But the hard part about that is oftentimes most problems aren't actually going to be convex for the lower level. So there's a bit of issues with that. There are actually some cases where it's been investigated as a multi-objective problem, as in like if you treat it as both of these objectives just exist at the same time. But the multi-objective nature has actually been shown not to really take into account that interaction that's happening hierarchically, that reaction. So that's kind of been treated as it's been kind of left to the side. But essentially there's classical methods that are used where they use, for example, branch and bound methods for solving both the upper and the lower level. There's also the case where you do it completely evolutionary. And in that case, you use an evolution algorithm at the top and evolutionary algorithm at the bottom, and you keep two separate populations, one for each of the levels, basically. And then there's also hybrid methods where both types of methods are used. Now, the reason for that is because of the fact that the evolutionary methods are incredibly intensive in terms of computation, and I'll come back to that in a moment. So the challenges that are present in these kinds of problems, first is that they may not even have a solution. So in the case of pessimistic optimization, the problem is really hard to solve in some cases, and in some cases it's actually not solvable. And that's been proven even in really, really simple formulations of like linear problems. So most of the research is actually dealing only with optimistic. Now, the structure of the lower level also influences the difficulty, as does the linkage between the two levels. So again, you can kind of think of this as similarities of what we talk about a lot in terms of landscape analysis. The structure of the problems actually has a strong relationship with how well the algorithms can perform. And in this case, there's this added dimension of, interaction that's nested. Now, we also have that in most of the simple cases, they treat it as, if you've got two levels, you've got a linear top level and a linear lower level, and that's usually how it gets solved. But actually, what's more realistic in real world is that you have optimization problems of different classes. So you might have like an assignment problem nested within a different type of problem entirely. It might be a dynamic optimization problem on the inside and an assignment problem on the outside. So these problems grow really, really large, really quickly, depending on how you think about it. And that's no good thing for when you're trying to solve these problems. And then, so you've got the standard issues of classical methods failing when problems aren't well behaved, like they're not continuous, they're not differentiable. And that also happens quite a lot when we're talking about real world problems. I mean, oftentimes we don't even know what's happening. We just know that typically it's not linear. And again, so I mentioned before how the evolutionary methods are computationally intensive. And the reason for that is because the way that it works. So if you imagine if this was a Kriging situation, right? So you've got this model and you're testing out these two points. What would usually happen is if this was a point that was being fed through by Kriging, you would then evaluate it, right? But instead of evaluating this point now, you're actually trying to get the minima of this optimization problem. So who knows how many solutions you have to evaluate within this space to get an approximation of the minima, right? You instead of having just a one-to-one where you feed this in and you get an evaluation, you now have to do a minimization in order to send back information upwards. And the same thing happens when you do it again. So once you change the upper level that's fed in, the lower level has to optimize itself first before it can feed it back up. So there's a lot of added computational effort, as you can imagine. And then as well, there's no standard of benchmarks for testing. So this is another issue that I think is persistent with something like this. Is it's very hard to actually determine, because of the interactions, what is actually going to be considered a good benchmark to test against. And right now, most of them are still linear. They create linear top levels and linear lower levels. Now, I'll come back to what I was talking about before about how we solve that real world problem as of right now. So the way we have it is we have a scenario which has inputs, and that input will then feed into a simulator, right? This simulator has a weapons assignment. So previously I was showing you the threats and then the weapons targeting them. that's still happening, but this time we just use a really simple greedy. At each time point, it's really greedy. It just sends the highest probability of neutralization out to defend, right? So there's only one solution. So unlike previously where I was showing you that surface doesn't matter because it's just using the classical method to solve it, and it just comes up with one answer. And so that will push it to the upper level optimization, which we have an evolutionary algorithm for, testing different algorithms for trying to actually optimize that. But essentially what comes out is we create an interpolation of the upper level surface. And this is essentially what we want to be getting. We want to be able to find the best version of this, but instead of using the laziest version or the greediest version of this, we want the follower or the lower level to actually be performing at its best. We want to find the interpolation of the upper level surface for when we do the best in the inner level, right? Because there's no point in finding what this upper level surface looks like if we're always getting like average. We're not utilizing the weapons the best that we can. So coming to the end of all of that, so essentially there's a lot of problems that come naturally following this, but the two most pertinent ones for me at first is one is how can we improve on how we're presently solving these problems. So I showed you previously that we have ours as our inner level is a branching bound method, and then our outer level is actually where we have our evolutionary algorithm. So how can we actually do that in a way that's less greedy, or takes into account at least a little bit more information than before? But also, and this is probably where I'm really asking for Optima to engage, is what techniques can we borrow from other optimization or machine learning methods? Firstly, for reducing the number of evaluations, but also for good enough solutions. So in this case, we're not really talking about, finding these absolute global minimums or, comparing these algorithms in that way. It's more so about finding something that can move that dial forward a little bit for solving these problems. There's research obviously into how to reduce the number of evaluations already. But even those are, they're not really proven to make a huge difference in the big scheme of it because these problems are so complex. And then how can we design test problems for good study cases is more of a research question for the field in general, I think, because presently the problems that are studied are generally just linear in the upper and lower level. But also how do we solve problems where there are different optimization problems at each level? And I think that's another important one. But I guess the questions that are most important to me today are, how can we approach solving this problem in a slightly more efficient way, or even just how can we do it better?